So I'm going to be giving you guys one lecture today, and then Pedro will be back tomorrow to tell you more about RG in the XY model. So today I'm going to be talking to you guys about classical Monte Carlo methods, specifically to study the XY model that we've been talking about for the last week. And we'll see more of this in tutorial. In tutorial, you should all bring your laptops because we'll develop the algorithm we talk about today in Python. So from the Python class, you should all have Python installed. And then you're also going to get a homework problem on something that's kind of an extension of the tutorial. So I've just kind of written on the first board just broadly what our goal is. So a major goal, just in statistical mechanics in general, would be to study various phenomena, like maybe different phases or phase transitions that can happen when we have many particles interacting, and in the limit where the number n of particles is very large. So this is a pretty big goal. So specifically today, we're going to talk about a strategy called Monte Carlo simulation. And we're going to specifically apply it to the XY model. Although a lot of what we'll talk about today is more general than the XY model, that's specifically where we're going to apply it in tutorial. So the explicit algorithms that I write out will be for the XY model, but they're actually not too hard to modify for other systems, such as an Ising model or an ON model, something like that. So I've written the main reference, this book by Newman and Barkema that I'm using. It's the first few chapters of this book, and that's a really great reference if you want to read about some of this stuff in more detail, because some things I'll just kind of introduce, but they talk about them really well in this book in case you want to read more. Okay, so the first thing that we're going to do, we're just going to briefly outline how we would calculate a general expectation value of some observable quantity just in statistical mechanics. So Pedro kind of talked about this in the first lecture, but we'll just review that just to make it clear what we're trying to calculate. Then we'll talk about why some of these quantities in certain models can be hard to calculate, and we'll see that Monte Carlo methods can help us address some of the complexity that we encounter in trying to do this. So I've just written here some of the key words that you're going to see throughout today's lecture. So we're going to talk about something called importance sampling, Markov chains, and then the specific algorithms we'll look at, Metropolis algorithm, and then a specific simple type of Metropolis algorithm, which just does single spin updates, and we'll talk about what that means. And then after that, we'll just talk about some more kind of technical implementation details about how you have to be careful when you analyze your data in these numerical simulations. Okay. So let's talk about our first point that I've written there. So in classical statistical mechanics, if I specifically think of the canonical ensemble, where I have my system at a fixed temperature, which is usually what we think of when we do these simulations. So I can calculate the expectation value for many different observable quantities. And in general, the way that I would do that is I would sum over all possible states that my system would be in. And I just do a weighted sum. And specifically, the way I calculate my probabilities is from the Boltzmann distribution in this case. And everything is normalized by my partition function. So I haven't made any reference to the XY model yet. This is just very general for any system with a general classical Hamiltonian. So just to remind you, that beta is my inverse temperature here. And in everything that we do, we're going to set this Boltzmann constant to 1, as we've often been doing already in the course. So this variable mu that I've written, this is just the notation I'm going to use to talk about some state, or we call it a microstate of our system. And our weights are defined in terms of the energy of that state. So E mu is the energy. Sounds like an animal, emu. Okay, so that's just our basic setup, which is maybe familiar from previous lectures. But the challenge comes in that we want to study this for systems that are interacting with many particles, and sometimes in various ways that can become more complicated or in higher dimensions. And sometimes it turns out it's pretty difficult to directly evaluate this sum. So to maybe just get across how difficult this is, I like to just think about the Ising model, which is a case where we actually know the exact solution. We know how to use theoretical techniques in order to do these kinds of sums exactly in 1 dimension and 2 dimensions. But in higher dimensions, we would need to use some kind of numerical technique if we wanted to get an exact solution. So we're going to just take a brief segue to the XY model, and then we'll come, sorry, to the Ising model, and then we'll come back to XY. So for my Ising model, I would be thinking about some lattice of spins where instead of allowing them to rotate from 0 to 2 pi, they can only just be up or down. Okay, so just to emphasize, these Monte Carlo numerical methods wouldn't even be needed in d equals 1 and d equals 2, but we could still use them to test that they work, and that's what we often do as a starting place in these algorithms, is we test them in a case where we know everything exactly. So if we didn't know the exact solution and we wanted to try to evaluate these sums directly, the most naive thing we could do is just try to actually compute this sum. So we could just, use these formulas, use the Hamiltonian, this Hamiltonian to calculate our energy for every state, and just directly try to do the sums for these quantities. Okay, so how many states would I need to sum over in this model if I wanted to, if I had, say, an L by L lattice so that n, in general dimensions, it would be L to the D. That's the number of sites that I have. Each one can be in 2 states. How many states would I have in total? Pardon? Yeah, exactly. Perfect. Yeah. So in this model, the total number of states I would have to sum over is some big exponential number. Now you can see why maybe it's clear why I wanted to start by talking about the Ising model, because this is a sum over a discrete number of states. For the XY model, I mean, the argument would be similar. It would still, I guess you could say, grow exponentially as we increase the states, but we would have a continuous number of states on each site. So this argument just is a little bit hard, not as obvious. So we just think of this simple case, the Ising model, and we'll see that even though this model is simpler than the XY model, it still quickly becomes very difficult to do these sums. So for the case of n equals 25, I talked to some people at PI who have tried to do these calculations exactly by doing this sum, by using a lot of sophisticated numerics. And the fastest they were able to do n equals 25 to evaluate these sums exactly was about a minute. Okay, so then if we know that that takes a minute, then we know that the time required is going to scale exponentially with the number of spins that I have in my system. So for n is 25, the time is on the order of a minute. But we can quickly see how fast this is going to grow. So if I just increase to 30 spins, that means this is going to take about half an hour to calculate. If I go up to, let's go all the way to 40, this is actually going to take 20 days to calculate that sum. But actually 20 days is not so bad. We have advanced, the reason it's not so bad is because you don't have to actually sit and watch this happen. You can spread this out onto many computers, right? We have these supercomputing clusters. We can run calculations on hundreds of nodes at the same time. We could actually do this calculation pretty efficiently. This wouldn't be too bad. But let's consider if we go up to 50, well, then this would take 60 years. Again, we could do this. If we really wanted to devote all of our energy, we could take a lot of computational resources. We could spend time dividing this onto many computers. We could do this. But if we go, okay, we could do some intermediate steps, but let's go all the way up to 80. Then this is actually going to be 7 times 10 to the 10 years. And this is longer than the age of the universe. So we don't have the resources on Earth to do this kind of calculation. And this is a pretty small lattice, right? This is n. This is not L. So this is just like a 9 by 9 lattice. This is really small. This is not really close to the thermodynamic limit that I want to access. Okay, so what this means is that if we were trying to study the two-dimensional Ising model, which again is pretty easy, we actually know the exact solution, we would be limited in these calculations to lattice sizes of 7 or 8 in my linear dimension. And this would be even worse if we try to study more complicated models like the XY model. So we need something better than just going through and numerically calculating these sums. Do you guys have any questions so far? No? So this is where we start talking about Monte Carlo methods. So far, this is not Monte Carlo, what I'm talking about evaluating these sums. This would just be a really naive way of trying to do this on your computer. So now let's talk about some techniques that we might do this a little bit quicker. Oh, and I forgot to mention, I'm going to upload my notes online for you guys. So in case you prefer not to take notes, I'm going to scan basically everything that I'm writing. Okay, so the main underlying idea of Monte Carlo methods is to incorporate some element of randomness when we do our calculations. So instead of summing over this whole huge exponential number of states, what I could do is I could say, well, I'm just going to choose m states, so mu1 up to mu m, and I'm just going to use those in order to estimate my observable quantities. And ideally, I'd like to have it so that m is much smaller than the actual number of states in my system. So this could definitely save me a lot of time if m is not too big. So, but actually the way that we choose them at random is where kind of the sophisticated element of the methods come in. And there's lots of different ways to choose m states at random. So can you guys see if I write just at the top here? It's more when it's down here, right? Where is it that it's like around here, right, that you can't see? So, okay, the most naive thing that we could do if we're incorporating this element of randomness is we could just choose our states completely at random with equal probability. So for every site on my lattice, I can think of the XY model now. I would go to every site and I would choose an angle at random between 0 and 2 pi. So I can do that. And this would give me some estimate for my observable quantities. So then, rather than calculating directly my expectation values, I would estimate them according to an estimator. And all I have done in changing this sum is that instead of it going over my whole state space, it's just going over some m, some elements m of this space. Okay, so does anybody see any problem with doing this in this way? Or there's actually situations where this works fine. Can you think of any case where it works or doesn't work? Does it just seem good?
States themselves are distributed according to some distribution. Some are more likely than others.
Yeah.
So if they're all equally probable, then this works fine.
That's right. Yeah, exactly. So, okay, and in which kind of situations typically would I have many states that are almost equally probable? So let's specifically restrict ourselves still to the canonical ensemble. Let's think about things as a function of temperature. Do you remember what do we expect at high temperature? When we do these arguments of considering energy versus entropy, we expect more entropy at high temperature, right? So many states are going to be highly probable at high temperature. So this is actually going to work okay at high temperature. So okay, but at low temperature, if I'm in, we can think of XY or icing model. We expect our states in very low temperatures to go to states where they're all aligned, right? But this is very unlikely for us to just choose that randomly. If we're just choosing states at random, what's the probability that we're actually going to choose one that's ordered? It's very small, right? So we're probably not going to sample the right states if we just do this flat sampling at low temperatures. And actually, it's so unlikely that we choose the right states that it would actually take around the same amount of time as doing these sums directly to actually hit one that is contributing with very high probability. If we take the limit of very small temperatures, we might as well just try to do the sums directly, because this is just never going to happen that we're going to choose the right state. Okay, so more generally, rather than just choosing these states with equal probability from a flat distribution, I could choose them from some other distribution that I choose. So okay, but if I'm going to be choosing my states from a different distribution, then I'm going to have to account for the way that I'm choosing them in my estimator. So then So then I have to insert these factors of the inverse of my probability distribution when I do these sums in order to account from the fact that I'm biasing towards choosing those by changing my distribution. Okay, but again, this is still really general. I can put any type of distribution that I want here. So here is where we introduce the first terminology point in Monte Carlo, which is called importance sampling. So the idea of importance sampling is just we want to have a way somehow of randomly selecting the more highly probable states the most often. So at very low temperature in our XY model, this means we more often want to choose states where all the spins are aligned or almost aligned. So ideally, what I would like to do is actually sample from the right distribution. So this would mean that the distribution W that I take my spins from is actually my Boltzmann distribution. And in this case, you can show that this formula takes a much simpler form where actually all that I have to do in this case is I just have to take the average of this observable quantity in all of my states, if they're really sampled independently from this distribution. But the actual matter, I haven't yet told you how we can actually select states from this distribution. That seems like it would be pretty hard because I've just told you that calculating this exactly for all of my states is a really difficult problem. But it turns out that there are some algorithms available that actually allow us to sample from this distribution without actually calculating it for all of our states. Question? Okay.
Actually, Lauren.
Yeah.
So what if you?
Sorry, one second. Let me just put this. I just couldn't hear you. Yeah.
What if you have some system where there are some very unlikely states that have, for some reason, like a huge value of the observable, then doesn't.
Let's see. So if right, yeah. So definitely, yeah. Right now, I'm saying this very generally that this is just for some general observable. But you're right. We actually have to be careful in what kind of observables we look at. And if they have some really weird behavior, we might have to come up with a more sophisticated algorithm. So yeah, we can, what I'm talking about today is more, I guess, just the simplest Monte Carlo algorithms that are available. But in practice, you actually design your algorithm both with respect to the model and also with respect to what you're calculating. So you might have to be careful about that for sure. Any other questions? Yeah.
You wrote a distribution W mu. We're sampling mu m from. So are mu m like W distributed random variables, or what are they? And then you wrote W at mu m. So what are we Are we evaluating W at mu m? I don't.
So, okay, what I mean by this is that, yeah, so W mu is some probability distribution that I can define as a function of, so how I choose my states mu is from that distribution. And then I'm choosing capital M states from that distribution, and I'm just labeling them mu. Like I'm doing this M times, and I'm giving them these M labels here. Does that make sense? So yeah, the subscript on the mu is just indexing. Like first I choose the first one. I'm just trying to have a label of which one was chosen at which time. But it's ideally this is all independent, so it doesn't really matter how I label them. I can choose that labeling in any order that I want.
W is a distribution on the space of states.
Yeah. Yeah.
Lauren, so
Yeah.
why are these the W's why are they to the -1?
Yeah, so I think this is a question that I think always seems a bit weird when you see it that way. But I think if you actually think about it, you could actually do a simple example where you write it out, and I think it'll make sense. It's basically just that if you're choosing something more frequently, then you have to account for that when you do your sums. So if you imagine if I'm trying to calculate the average of some numbers, like just some numbers that are all different, but for some reason I choose to pick one number way more frequently than other numbers, well, then I don't want to actually just have that number have the same weight as other numbers, right? If for some reason I'm choosing it more often, I have to account for how much more often I'm choosing it in my sum.
The important sampling formula, because of W is equal to E, it's going to cancel. You're going to get. I don't know why it's the inverse. I think the more important it is, I mean, the bigger W is, it should be like contributing more.
Okay, so let's look at, I don't know, maybe if I explicitly write out the example I was saying, maybe it'll be more obvious. So let's just say that I'm trying to calculate the average of some set, and the elements in here are like 1, 1, 1, and then I'm just repeating some things, and then I have something like this. Okay, so then the average I could calculate as, I could just directly sum all of these things over how many elements? 1, 2, 3, 4, 5, 6, 7, 8. I could do it like this, right? Or I could do probabilities, right? I could say it's 3 over 8 times 1 plus 1 over 8 times 2 and then, so this case, yeah, I can just write it like this. And so this is like writing, how do I put it in the same language? I've done this so many times before, but now I'm like thinking on the spot, and I'm maybe going to get it wrong. So this case, okay, I guess this case we don't have our Boltzmann distribution. So then here we're summing, this is my, sorry, let me think for a second. Right, I can think of this instead as some set with just the unique elements, 2, 4, 6, and 9. And the weights here would be 3 over 8, 1 over 8, 1 over 8. And then, right, okay. And then the point is that here, so what I actually want to calculate, this should actually be my P, because this is the probability distribution that I want to. So if I actually want to calculate this average, this is what I want to get. But if I were to just sample these states at random and I didn't account for this weighting, then I would get the wrong thing, right? So then, if I were to just choose these arbitrarily, I would never just like happen to choose this one more often, right? But I guess in this case, it's actually the other way around because, sorry, then, right, okay. So what I actually want to do is calculate it from this primed distribution here, like this. But the way I'm going to calculate that is sampling from this guy, right? Sorry, it's actually really not so complicated, but I just didn't think about it beforehand. Maybe let me think about it and we'll make it a tutorial problem today. Just because when I think about math on the spot, I just make mistakes, but it's actually very simple, but we'll for sure do it as like the intro problem on the tutorial and you'll get it right away for sure. So just trust me that it's right and I promise it'll make sense. I'm just like trying to think. So let's erase this from your notes because it's just very confusing and we'll talk about it later. Okay, so assuming that this is the right formula, especially if I'm selecting from the Boltzmann distribution, so that then when I calculate an observable, I'm just directly taking the average in those states. Now we're going to introduce the concept of Markov chain Monte Carlo. Okay, so the idea is that we're going to choose our next state in our chain of samples based on the state that we're currently in. But the way that we transition between states has to satisfy certain properties. So have any of you heard of Markov chains before? Is there anything this makes you think of? Any properties you think you might have to satisfy?
Should not depend on the previous states.
Exactly, yeah. So kind of as you can see from the notation here, so it only depends on the state that I'm in and the state I'm trying to move to. It doesn't depend on any of my earlier history of my states. So in what we're studying here, it's very important that our transition probabilities don't depend on time because we're trying to sample an equilibrium Boltzmann distribution here. And the last thing is that, of course, if we're in a state, we have to transition somewhere. Even if that transition is to the same state, we still have to go somewhere. So the sum of all these transition probabilities has to be 1. So what I'm going to call this notation-wise is that the resulting set of states that I get is called my Markov chain of states. So many different Monte Carlo algorithms design these transition probabilities in different ways. But no matter how you choose to design your algorithm, you have to satisfy two conditions. So the first one is called ergodicity. What this means is that it has to be possible to somehow, at some point in time, reach every possible state in your system. Okay, so this doesn't mean that my transition probabilities can't ever be 0 for some pairs. It just means that there has to be a chain of intermediate states so that I could transition from mu and maybe a bunch of states in between, and then eventually get to my state nu. And we're going to see that the algorithm that we are going to look at today, it actually does satisfy this property in principle, but sometimes in some algorithms that technically work, but in practice aren't very good, the time that it takes to reach between any chain of states can be exponentially long. So this can also be a problem in some situations. But to have the algorithm just work in principle, this is something we have to have. And better algorithms are going to have a shorter transition between two equally probable states, basically. Or just a shorter transition time between two highly probable states. They don't have to be equally probable. Sorry. Okay, the second condition I need to satisfy is called detailed balance. So what detailed balance says is that if I'm trying to sample from some distribution mu that's not changing in time, then the rate that I transition into and out of some state should be equal, because otherwise this distribution mu would be changing with time. So since we're looking at cases where this w, doesn't change with time, we need to have this balance. Sorry, actually, what I'm writing down is not quite detailed balance yet, but this leads to detailed balance in a second. So I have to have this satisfied for every possible state mu. And one way to have this is the detailed balance condition.
Sorry, Lauren.
Yeah.
It's,
Did I make a mistake?
maybe there's a mu, because mu is not symmetric. Like, I think that we might be missing a mu.
So this is all the possible ways I can go into mu. So I would start in some nu, and then I would go into mu from there. So both cases I sum over nu.
Okay.
Because it has to be true for all mu. And then here I start in mu and I transition somewhere else. Yeah. So this is actually turns out to be a good way to satisfy this property, and it's called detailed balance. Okay, so in our case, we said we specifically want a sample from the Boltzmann distribution. Then it turns out that we can choose our transition probabilities in any way as long as the ratio of them going from a state to another state and back satisfies this equation here. Okay, so when we actually implement our algorithms, what we actually do is we introduce some new notation for these transition probabilities so that we break them down into two factors. So again, this is just notation. So I'm going to actually say that to transition from a state, I'm going to break this down kind of into two steps. So first I have to select that proposed move. And then I have to actually accept it. So that just means that I can really propose any move that I want. I don't really have to, in principle, if I want, I can just not be very careful about what moves I propose. But then I just accept them according to this distribution. Or in lots of cases, we actually put a lot of care into how we select these. But there's lots of options available. So again, when I say selection, it means the probability that my algorithm will propose the move. And then acceptance probability is whether I actually accept to do that. after it's proposed. And ideally, what we would like, if we have a choice, is that our acceptance probabilities will be as close to 1 as possible, because it would waste a lot of our resources if we just keep proposing moves and then not accepting it. And just to write it explicitly, from detailed balance, this is what we have to have. If we just solve, all I've done is just solve for my acceptance probability. Let's say that for some reason, I'm just taking a really simple example, which we would not use random Monte Carlo for. But let's say that I want to compute this sum where I'm just going to take the example I had before. My S was this set, and let's say that I'm going to do it. It's a slightly different example. Okay, so let's just say that I want to compute this. So one strategy let's just say S. Select from, my first strategy could just select from S uniformly at random. This would maybe give me, I'm just going to call it Y. And I'm going to do this n times. OK, so maybe the first time I select randomly from that set, I'm going to get like 8. And then I'm going to get 2, 1, 9. OK, I'm going to get some random chain of numbers. But I'm going to expect that as n goes to infinity, that this is S bar. And in this case, it's just going to be 1 plus 2 plus 4 plus 9. I'm going to expect that if I do this many times, then y mu over n, I guess. So if I just were to just select with equal probability from this thing, then I would get a good estimate for my S bar here that I'm trying to calculate. But maybe I just, for some reason, I can't choose from this distribution. So in this case, I'm selecting using this distribution here. But maybe I can't do that. Maybe for some reason, I'm going to use the weights like this, that was the example I gave before. Well, then when I take n points from this distribution, from S, these are the weights corresponding to S, then the samples that I'm going to get 1 way more often, right? because I'm weighting this more, I'm choosing this more often. I'm going to get something like that, right? So then, if I were to just sum these samples, this is not equal to S bar. And it's also, if I were to multiply by these weights, I would be making it worse, right? I would be even more biasing towards the 1, even though I've already selected it more times, right? So this is also not going to work if I do. So what I really need to do is use these inverse weights to account for the fact that I'm biasing towards those states. Does it make a bit more sense now? So I think maybe the reason it gets confusing is because in the examples we're looking at, we have this additional factor of our Boltzmann weight that's different for every site. But really in this argument, you can just think of that as being sort of part of S mu somehow. So we're just trying to compute this sum in some way by using some intelligent weighting. But if we're biasing towards a certain state, we have to account for that bias in kind of this inverse way in the sum. Does it make more sense now? Yeah, okay. Okay, so that was just an aside to address that earlier question. So now let's go back to thinking about this detailed balance constraint on these transition probabilities that for now it seems pretty arbitrary that I've just chosen to break them up into acceptance and selection probability. Okay, so as I said, ideally we would like an algorithm so that our acceptances are very high. But this is not always so easy. So this is why we break it down into this G times A. So the general idea of a metropolis algorithm, and there's actually many types of metropolis algorithms, is that we want to make sure that if we're going from mu to nu, we can also go back from nu to mu. And one of those moves is going to have probability 1 of being accepted. So in general, a good strategy to just ensure that at least moves in one direction are always accepted is we use this. Okay, so now we're finally at a point where we can actually talk about a specific algorithm for the XY model. Okay. So what we're going to do now is we're going to talk about the very simplest algorithm I could think of for proposing my Markov chain, which is just that if I'm in a given state, I can get my next state by just choosing one spin at random and rotating it in some random way. Okay, so the way this is going to work is I'm going to have my lattice of spins. I'm just drawing 4 of them here, but this can be a really huge lattice. In the tutorial, we're going to consider 2 dimensions, so a 2-dimensional L by L lattice. And the moves that we're going to propose to move through this Markov chain of states is that I just choose a site at random and I randomly rotate. I propose rotating that spin. Okay, and in the algorithm that we're going to do specifically, we're going to just choose this to be any angle, but you can actually be more sophisticated about this. You can kind of bias towards small changes if you want. And depending on how you do that, you have to modify your algorithm. But in the tutorial today, we're just going to do something very naive where we just choose states and we propose rotating them by just any random angle that we choose from uniformly between negative pi and pi. So then, in this case, the selection probabilities, well, I only have a possibility of selecting moves that are within one spin rotation of my current state. So this is just some constant, I'll say. And if they're different at more than one location, then I'm never going to directly select a move from mu to that state nu. But still, I would hope that I have ergodicity so that eventually I could move from any one state to the next. But it would take several moves to do that. Then, from the Metropolis algorithm, what I just have in this case and I think a good exercise is just convincing yourself that this is true, that what this Metropolis algorithm, which satisfies deep-tailed balance, tells us is that if we propose a move where the energy of our system increases, we still accept it sometimes, but with a probability that depends on the Boltzmann distribution. And if this move keeps our energy the same or decreases it, then we always accept it. Okay, so I just want to summarize here all of the steps of this algorithm. And this is exactly what we're going to implement in the tutorial today. Okay, so the way that this works in practice is we first have to initialize our system to some random state. So mu1, we actually just choose it completely at random. Okay, then in order to propose a move to a new state mu in my state space, I'm just going to choose a site I at random out of all the n sites. And I'm also going to choose a random angle to rotate that spin by. Okay, then I'm going to calculate how much my energy would change if I were to accept that move. And then ultimately what I want to do is follow this condition to choose whether I accept that move. So if the energy change is negative, I'm just going to definitely accept that move. But if it's positive, I need to accept it with some probability. So the way we do that numerically is we use random numbers yet again. So I'm going to generate some random number, and then this is where I choose to accept my move. So again, if my energy change is negative, or if that random number is less than this Boltzmann factor that I derived up there, then I'm going to accept this move, and my mu m plus 1 is going to come from this rotation here. But if neither of these are satisfied, then I'm just going to reject my move, and I'm going to stay in the same state. Okay, do you guys? Yeah. Question.
If we stay in the same state, does it mean we have the same states in the Markov chain
Yeah.
in a row?
Yeah, exactly. Yeah. So do you see any problems with that, actually? Anybody? With like, definitely when we move from one state to the next, they're going to be very correlated, right? They're going to be the same almost everywhere, except maybe at one site, right? Whereas in lots of our initial assumptions, we were assuming that our states were taken from independently from our Boltzmann distribution, ideally, right? So this is definitely not the case. We have a lot of correlations in our sample. So there's a few problems. Yeah?
I thought we said that A mu to nu is equal to that Boltzmann weight if E mu is greater than E
Uh-huh.
or whatever.
Yeah.
So why do we choose the random number between 0 and 1?
Because that's our probability of accepting, right? So how often am I going to accept it? Let's say that
Oh, I see.
yeah, makes sense. If it's 0.7, then 0.7 of the time I'm going to accept it. So I generate a random number. Yeah, makes sense? Okay, so there's a couple problems with just naively using this algorithm. One of them is that you're not really getting independent samples. And the other problem is that we're starting from an initial state, right? But let's say we're at very low temperatures. A random state is not really a very good sample from what we expect to have at low temperatures, right? At low temperatures, just for example, we expect everything to be ordered. We're not really going to be getting very good samples at the beginning. So there's just, this is where I wanted to talk about a couple of technical details. The first is called equilibration, and basically what this means is that we actually just usually throw out a bunch of our initial samples because they're not really from the distribution we want. Okay, so there's actually a way to prove that if you use this algorithm, you'll eventually reach the right distribution. And again, in practice, sometimes it takes a very long time. But in the example we're going to do today, it doesn't take very long. So you can read this section of the textbook I mentioned, and they explain why you're guaranteed to eventually reach the right distribution, but we only have a few minutes, so I'm not going to explain that now. But the idea is just that if we actually were to look at the quantity that we're trying to measure, often we can actually tell that we're not sampling from the right distribution. So if I were to plot just the values I get from my quantity that I'm trying to measure in order, so what I mean by Markov time is just putting my samples in order. So starting from my first sample, second sample, etc. So if I plotted this quantity, I do expect random fluctuations because I'm not just going to get the same value, especially at high temperatures when I have a lot of entropy. I'll get slightly different values for different samples. But at the beginning, these will really not be characteristic of the actual noise that I statistically expect. So here, so rather than just directly calculating our estimator by just summing over all of these samples, we don't really want to use these in calculating our average because they're not very good. So instead, I'm sorry, this is like four levels of labels here. Q, mu, T, E. So sorry about that. I like labeling things a lot. So I hope it makes sense. Oh, this is plus M. So. Okay, so this last thing we'll talk about is just this issue of how we would deal with the correlations in our data. Because we might want to calculate error bars on some quantity, and in order to do that, we're usually going to want to have independent samples. And this algorithm I've told you is definitely not giving us independent samples. There's really big correlations from one configuration to the next. So what we would really like, as I said, is for our states, our sampled states, to be statistically independent, but they're not. So the time that you would need to get independent states, this is called the autocorrelation time. It depends on many things. It depends on the details of your model, the algorithm that you're using, and the temperature. So again, I'll refer you to this book I mentioned. They talk about how actually given measurements in your system, you could calculate how long the autocorrelation time is. But in our case, we're not so worried about having independent samples because we're not going to be calculating error bars too rigorously. So we're just going to do something pretty rough in our calculations. We're just going to do on the order of n updates before we add something to our Markov chain. Which again, they could still have correlations, and depending on the temperature especially close to the critical temperature, we're going to probably still have pretty big correlations in our data, but we'll still get a pretty good estimate for the quantities that we're looking at. And if you want, on the homework, if you want to go above and beyond, you can actually calculate the autocorrelation time, but you don't have to. So what we do in practice is before we actually record something and call it mu n plus 1, we don't actually do one single spin move, we do on the order of n. So in the code that I'm going to give you to start with this afternoon, you're just going to see there's a loop, a for loop over n in there, and that's what that's doing. It's doing a sweep. Okay, so I just want to make a couple of really quick notes, and then I'll let you go. So the first is that this algorithm is just really the most naive one that we usually start with in Monte Carlo, but there's lots of more efficient and better algorithms that'll address some of these correlation issues in a better way. So there's also algorithms that instead of just updating one spin, they intelligently update many spins at the same time in connected clusters. So there's two algorithms for the types of models that we're looking at for Ising, XY, and ON models that people often use. The first was developed by Swenson and Wang. And the second is by Wolf. This one I've used many times in my research. We often use Wolf clusters and variations on these models too in classical Monte Carlo. Okay, and the last thing that I want to say, so you guys aren't going to work with these cluster algorithms, but I just think it's nice to just know that they exist. So I just like to note that. So just to tell you what we're going to do today, we're going to use this algorithm to plot various observables as a function of temperature. So So when I say this algorithm, I mean the single spin flip metropolis algorithm. So for example, we're going to study the energy as a function of temperature in this model. And we're also going to visualize configurations. And you'll actually be able to see vortices in these simulations, which is really fun. I think it's fun, at least. So when you do these updates, you're going to see that your very simple single spin flip metropolis algorithm is going to give you configurations with vortices, and you'll be able to see them. So on the question that you're going to get after the tutorial today, you're going to use this code from the tutorial to estimate the critical temperature in the XY model. So we're actually going to get a better estimate for the critical temperature than we get from the RG. So doing all these complicated analyses that Pedro has been doing in RG, they're going to give us ways of estimating various properties and maybe studying the theory behind them. But to actually get the best estimate that we can of where the transition happens, these methods are actually going to give us the best way that we can of studying those. OK, do you guys have any questions? Nothing. OK, we'll see you this afternoon.